Работает? Ура, работает! Ну что ж, настал момент, которого мы ждали так долго. Сейчас свой доклад презентует Арсен Kostenko, Senior Software Engineer at Media Intelligence Team in Netflix. Он будет рассказывать про subjective aspects of data. Вопросы сможете задать в конце. Арсен, пожалуйста.
Hi. So, before we begin, I assume there are not just Ukrainians in the audience. So, which do we go? We can go English. Anyone English? Ukrainska? Okay, I'll stick with English. If there is something blurry or you don't understand anything, just let me know. I'll try to explain. Now, have you seen Irishman yet? No? Well, the critics say it's a great movie, so go watch it. I haven't watched it myself, but I did similar type of talk several times already. And every time I do this, I start with this funny punchline, which goes like this. Gradient descent can write code better than you. I'm sorry. Now, this is a real tweet by a real person, and the person is this. Do you know this guy? And by the way, I assume that you know what gradient descent is. Is that the case? Does everyone understand what gradient descent is here? Okay, nice. Yeah, well, that's much better than like a week ago at DevOps Ukraine. So I had to go and explain what Pohitna is and how it works. Okay, so this is good. Now, what's interesting about Andrei Karpathy is that he is being not just influential in the academia, but also in the industry. And when he's asked about the difference in the worlds between academia and industry, he goes like this. Oh no, well, so the idea behind one and the other world is that for academia, you care most about the algorithms. You care about the new neural network architecture. You discuss that, that's what you present at the conferences and things like that. For people in the industry, the main question is data. How do you get it? How do you process it? How do you manage it? And how do you make sure that the data that you had for training is the same that you're going to be having for the actual inference when you're running models in production. Now, this is important because I'm going to be talking about the subjective parts of data, and those things are, it's hard to measure them. It's hard to measure them in principle. I'll be talking mostly about this paper that we're going to be presenting at, I believe, ICCV. I might be wrong on the conference name, but that's something that's going to be presented this year or next year, but it's already published on arXiv. So, okay, I am a software engineer. I'm not a data scientist. I know enough to talk about this, but if you dig deep enough, you'll eventually, find my rock bottom, where my understanding is shallow. With that in mind, let's carry on. So first of all, how did we arrive? Why Netflix is doing computer vision? We started really simple. We started with the problem of analyzing media for encoding. When the movie comes to Netflix platform, the first thing, usually any media ingestion pipeline has a step which is called analysis, inspection. This is where we check whether the file is there. We started just simple as that. Is the file there? Is that a zip file? Or maybe that's some different type of file. If that is, then let's unpack it and try to look a little bit deeper. So we started going deeper and deeper. And the next step was, let's make sure that the container format is okay. Let's make sure that the container format is structured the way we expect. So those were more technical checks. Now, as you go this path, you already have some infrastructure in some place to run some analyses on media. The very next step was just to make sure that that media has good quality of content of video. Some of those things are like, make sure that there are no dead pixels. Cameras are physical objects. Because of their physicality, there might be scratches, there might be dust, there might be some other things like physical damage that manifest as the pixels that have very low color intensity. They carry very little color information. The problem with that is that the more you encode, the more those spots persist. They never go away. You can think of them as like a tumor of media encoding. So you better know about them as soon as possible. Now, for this particular talk, I'm not going to be describing that use case. I'm going to be describing something else, what we call product artwork. So when you go to Netflix, how many of you actually use Netflix? Okay, so you know the UI, you know the screen. When you go there, there is this list of movies, what we call Lolamo. And when you go there, every movie is represented as an image. Now here's the problem. We have many movies. Which movies to show you is the classical problem of content rating. And this is done roughly like, what movies have I watched in the past, then we try to correlate that with some group, we see what that group would like to view in the future, and we make a prediction for a particular person. That's easy. Now, the other part is that there are also many possible images that you can put on, on the artwork, on this small image that represents a movie. And for every movie, you need at least one image. That's fine. So you make that selection once. But then comes the really complicated thing, the viewers. And people, they complicate everything all the time. Every person has their own preference. Like, when someone advertises Pulp Fiction movie to me, I might be more susceptible to click on that if I'm showing the image of, I don't know, John Travolta. But if someone of you is there, maybe you are more susceptible to clicking that. You're more excited to click on that movie if you are showing Uma Thurman. So we need to know, which preferences people have. Now, this itself is still a recommendation problem. Where we come in is, okay, so we have, let's see if this works. So this second block, is repeated multiple times. Why? Precisely because we have to make many images. So if you have to make 2 images, you would have this decision twice. If you would have like 10 images, you would have 10 times a decision to make. Now, every time you make this decision, essentially, the easiest way is to go just look at the content, pick a frame that is beautiful, and say, this is one candidate, no, this is the other candidate, and so on. Now, in all this, there is a critical question, an image that is beautiful, and that is subjective. So how do we pick a beautiful image, or how do we help a human operator get beautiful images? Get them as many beautiful images up front so that their selection, their choice is easier. They don't have to refresh this page multiple times or watch the whole movie all through. Now, this is a UI that we built. Essentially, what you can see here is that when we pick a frame, this character, they have their eyes open. They're more likely to be smiling. They're more likely to be centered according to the rule of thirds, what we call правило золотого перерізу, and other things. So every time you have one of those images, it is not just blurry. So this one is maybe not the best one, but this one is much more exciting because the character is looking at you, and if you present that to a user, they would be excited about the content itself. So this is the first problem we're dealing with. The second problem we're dealing with is banner selection. Banner selection is Lolamo. Let's go back to Lolamo. In Lolamo, the first thing you usually see is this big image that represents the most advertised title right now. Now, this banner should also be beautiful, but not only that, it also needs to have some internal structure, some logical structure. In particular, there has to be a big space that is visually appealing, but there also should be a space where we can put our controls. Text about the image, which will go roughly here, and then the controls like a play button and something like that. And also, there shouldn't be anything of value down here, because that's where we're gonna place other, like other ads of other movies. And if there is like a text there, if there is a monster jumping out, or if there is something that is crucial to the story, you don't want that to be covered, because the effect is going to be opposite. People wouldn't like that. So here's the problem. We have beautiful image that is subjective in the first place, but also that has a structure that is roughly objective, but how do we describe this? So here is an example of what that actually would look like. And not only this, sometimes this is not the only structure. Sometimes it's reversed. Sometimes if you have a language that goes, not left to right, right to left, you would have to reverse the whole thing. You have to reverse the logic. And now, this thing is second biggest use case that we're dealing with. So, going back, formulating the problem, we need to find out what is structure of an image, what is composition, and also make some judgment whether that composition is something we're actually looking for. Now, let's go to the hardcore details. First of all, our biggest challenge here is we need to know that both small and big details are preserved, and the structure is something we're actually making our inference on. It's not that we're just, selecting images from the particular data set. We want to make sure that the images we're selecting are adhering to the structure. Now, the biggest thing in here is that it's like two parts of the problem. One part is we need to have those details ready. We need to have everything that we're going to be inferring our decision on ready by one part of the network, and then the other part of the network will actually make and drive the decision for us. So we would like to capture the visual elements in a way that is easy to reason about later. Now, the whole thing is that we try to break this down into two pieces. First piece is where we capture the low-level details. The low-level details is like, imagine the picture of the boy that we saw previously. We don't want to lose the fineness of his suit and the fineness of the outfit that he's wearing. If that somehow becomes more blurry, maybe because of the motion blur, that's something we would like to discard. On the other hand, we would like to reason not just about the tiny things, we would like to reason about bigger things. Like, we would like to have the color composition on his suit, on his hands and the rest of the suit match. If that somehow is distorted, we would like to, not promote such images. Now, for the first part, we choose DenseNet. How many of you understand what DenseNet is? Because bigger part of this talk is going to be describing DenseNet, and maybe you will help me. If I'm mistaken in some place, let me know and we'll figure this out. Now, short introduction to that. DenseNet was proposed in 2017 by Cornell researchers and I think Facebook AI research. And the idea is that you somehow propagate more information through the layers. That's exactly what we want, because we want to capture those finer details. We want to capture the information from the initial input as long as possible, preferably up to the very end. That's why it fits our bill. So, short retrospective, how much do I have to go into all these? I believe that one is clearly understood here. So is AlexNet. How about VGG and Inception? Do we understand what benefits those architectures brought to the table? Okay. ResNet. Do we have to go into there? Okay. So just to make sure that the last part was like not really, really affirmative for me. So just so that everybody is on the same page. The main benefit that ResNet brought was that you are addressing the gradient explosion or decay problem, where your network can become much deeper and you can do much more with that. All right, so standard connectivity looks like this, and then you eventually move to the dense connectivity. The dense connectivity is where you essentially propagate your input to all the other outputs. Okay, now the trick with that is that if you just concatenate the channels, eventually you'll have much more computation. So you somehow need to limit the output on every single layer of the dense net. Now what happens is that if you do like this, you'll eventually grow your computation. So in order to address this, you are, okay, not to address it, but essentially to solve for this, you first do the regular batch normalization, ReLU, and convolution 3x3, but then you actually do this optimization where you limit the number of channels, so that one-by-one convolution helps you reduce your channel depth, and therefore you can always append your input to the output and make sure that it's still propagated well. In order for the dense net to be still able to downsize, you compose the blocks. So in our case, we had this one removed and replaced with 2 additional convolutional layers, so that we would be training the whole thing on ImageNet, and the last part will be trained on our specific data. The advantages I'll skip very fast through. You have better computation, you have better propagation of the signal, and you have deep supervision. Now, the other thing that we added was dilated convolution and spatial pooling, spatial pyramid pooling. So here, the main idea is that once you are composing your inputs, you want to go, once you have your fine-grained details, you want to expand, you want to go out and have the bigger parts captured, like when the color of the suit, it should match. In order to do this, first you do the dilated convolution, which allows you to take the same input and do, instead of reducing the output size every single time, keep the input the same, but do the convolution on the bigger space. Now, the interesting part that kind of was added by us is that we have this pyramid where we actually stack them together, and then this is the magic. This is where it becomes the source for the reasoning. So once we are, so this part is the output of our dense net. Then we do the whole stacking and spatial pooling. By this time we have like I think H and W in our case are 300 by 300. So this is the matrix that completely describes our image. Now we flip it and we treat it like so. This part becomes the feature vector, and this one becomes the number of features that we're reasoning about. The next thing, we turn this into the self-similarity matrix. So we essentially try to compose that as a graph, and then try to do the reasoning on top of that graph. Now, why do we do the reasoning and why do we do the graph? This is precisely because we want to have the logical composition of the image. preserved, and we want to reason on top of the composition. Doesn't look beautiful, but neural networks are still able to infer this as a person. In fact, it could be a person with a higher confidence than the regular input. Now, the problem with this, and this is something that was tried by grandfathers of neural networks. Jeff Hinton is struggling with this, and the idea is you want to make sure that neural networks capture not just particular features, they capture their composition between themselves. Two possible solutions to that proposed were capsule networks and stack capsule autoencoders. Both have their merits, but they're both compute intensive. It's not something we can leverage out of the box. So what we did was graph neural networks, graph convolution to be precise, and because in the interest of time, what we essentially do is we try to convolve graph with itself so that we extract the features that are closer and closer correlated, and we reason not on top of one particular feature vector, but on their combination. So this is probably the final poster from the whole talk. This is where we get the output of our spatial pooling. Now, by this time, we have particular features, and the very next step is we actually do exactly 3 levels of convolution. So we try to compose each feature with its neighbor, then that cluster with its neighbors, and finally the neighbors of the clusters with their neighbors. Eventually, what we arrive is like a high-level components of the graph. Some results. We were using two data sets that are open, because you need benchmark. You cannot just go out there and say, we have our own data, we're going to be doing this, and we will not show you the data. So we first went for the data that is open and available, and with this, the claim is we achieved state-of-the-art by beating the existing state-of-the-art by 1-something%. Doesn't sound great, but that's more than statistically, that is statistically relevant, and that's what was good enough for us to actually get the paper out. Now, the second data set is a little bit more interesting because this one is not composed by, the first one is composed out of Flickr images that are rated by the human audience, user-generated content. This one is more like curated by professionals. So this one was important to us as well. Now, so essentially we have 3 big pieces. We have DenseNet, we have ASPP, and then we have graph convolution. The question is, how much of those pieces is actually important? Can we just replace any one of those and say, that could be good enough as well? And the answer is no. The answer is no, we cannot replace the DenseNet, because if we do, like if we replace it with ResNet or anything like that, we have the drop in performance. Can we drop the spatial pyramid pooling? No, because with that we also have the drop in performance. Can we drop the graph convolution? Again, no. So every single of those components is essential and moves us towards better understanding of subjective quality of the picture. Now, here are some results. The test image, this is what it would look like after the DenseNet. This is what it would look like with DenseNet plus ASPP, and finally the graph convolution. So essentially you have the attention expanding not from just single place, but also to like global features. This is especially good here. All right, and again, this is not my work. Most of that was done by the team of researchers. I'm just a software engineer who's presenting the work for them. Thank you.
Thank you, Arsen. For such a great topic. So here's the reference. You will send a presentation lately, so any questions? Okay.
Thank you for the great talk. I'm wondering about the data that was used for supervision, how it was collected. So what were the labels like? Could you describe this?
Yeah, so there were multiple things. First of all, there was a pre-trained dense net image net. That's clear. Now, I didn't talk about the cost function at all, if you noticed, which is an important part. So for us, eventually we had a collection of images that were essentially of two classes. We used binary cross entropy, where we said that this one is beautiful, that one is not, beautiful not, and then eventually the data from those benchmarks was a big part, plus some of the proprietary data that we have on our own assets.
So actually there were like data annotators who tagged either the image is beautiful or not.
Yes, yes. Some of them.
Can you give maybe some advices how do you tackle with the situation when you know, all this is subjective? So if you just run 1 million images through like 10K people.
That is a really good question. Thank you. Now, if you go and look at our paper, I think this is the one. If you go there, you will see that the visual results that we present are actually just the two tiers. So there is the top tier, like the most beautiful images selected by our network, and then the lowest level quality images. We don't show anything in between because that gets really blurry. So essentially, for us, we're trying to push the middle ground as much as possible out and just make sure that we're picking the 99th percentile of the images and hoping that that correlates well to the aesthetic quality of the image.
Thank you.
Any more? Nobody? Ah, okay. Thank you for the talk. Could you, I joined to a previous question and wanted to ask you, could you tell me more about features that you distinct for aesthetic accession, estimation? So how you detect this beautifulness?
Yeah, so if I understand your question correct, like what features of the image have the model learned by itself, which correlate to our understanding of aesthetics and beauty? Okay. Yeah. One thing that we were really surprised the model learned, they learned the rule of thirds. So usually when the object is there, the model does not pick images where the most salient image is front and center to the image. It usually picks images where the most salient object in that image is somewhat, a little bit to the right or a little bit to the left. That was surprising us. Now, the other thing is we were really interested in estimating the focus depth. So, when you have a zoomed in picture and something is really, really sharp in the center, but then everything else is blurry, that one came through as well. Does that make sense? Does that answer your question?
I think yes. Можно на русском будет быстрее?
Sure. Go ahead.
Просто действительно вопрос очень субъективный, да, и сколько бы ни, то есть тут все равно какой-то уровень, скажем, нейросеть получается, вообще эта модель получается, то есть у нее субъективный свое восприятие получается в итоге на основании оценки вот тех экспертов, которые были, да?
Так, я згоден. Тобто По-перше, це все екстраполяція оцінки людей і експертів, які до того щось зробили з даними. Це факт. Друге питання в тому, що ми не пропонуємо результати одразу. Перше, що відбувається з цією моделлю, ця модель допомагає операторам, які вже є creators, які є творцями, які є митцями, обирати щось. Плюс до того, далеко не весь час вони просто обирають. Деколи вони беруть фотку і з нею ще щось роблять. Вони там фотошоплять її трошечки, вони там десь її підсовують, щось таке відбувається. Тобто це не просто, типу, хтось обирає фотку і людина каже так або ні, ми підбираємо те чи ні. Це просто допомагає зробити тих людей, які обирають ці box art, artwork і банери, зробити їх трошечки більш ефективними, щоб вони не дивилися весь фільм одразу, а давати їм пул зображень, які достатньо хороші, щоб вони почали з ними працювати. Це схоже на відповідь?
Да, я поняла. То есть тут для конкретной задачи оно очень хорошо решает. То есть не для, не широкое применение получается.
Ну, наприклад, я би цю модель не ставив в Pinterest для того, щоб він рекомендував там вам стилі. Це моя суб'єктивна точка зору.
Спасибо, интересно.
Hi, Arsen. Thanks a lot for the presentation, and it was charming. and also I had a question. I was wondering, how did you probably test your models in production? I mean, how did you probably you have to get a feedback from the end users regarding the pictures, and especially it might be different for different regions, as you note, for languages, and this beautiful perception is also definitely it's different for different countries, or it's not. That depends. Yeah. Basically, how did you improve on your models based on the feedback from this second layers of the people who's working with images and of the end users, if there's.
Yeah, thank you for your question. That's important. The flywheel effect is usually important. I'm not sure we're doing that. I'm not sure we're doing that yet. Mostly because this is an internal tool, because this is something we're doing for ourselves, it always gets not as much treatment as something you present to your actual customers. So I think there will be more work. I hope I'll be back talking about that work in the future. Right now, there's not much to share.
So, one more, okay.
Thank you for your talk. Can you please say, did you try not to use binary cross entropy, but to compare two images, just to say this one better than this?
This is okay.
And if you will go this way, it's immediately give you a chance to use users' feedback that you said just 1 second ago from the choices.
Yeah. So great question. Thank you. Now, have you heard of VMAF? No. So VMAF is a Netflix-specific quality metric of an image. It's a subjective, perceptual quality metric of an image that helps you, correlate the quality of encoding, so the bitwise quality, with the perceptual quality, human quality. The example I used to bring up a lot is cartoons. If you have a cartoon like South Park or I don't know, BoJack Horseman, you drop the quality bitrate twice, 50%, and watchers, viewers barely even notice because it's a cartoon. You have an image where there is a face. You drop quality like a little bit, and everybody knows instantly. So this thing is important on how do you compare two images. Now, if you want to compare two images and there is no human in the loop, there is no human to actually tell the truth between them, you need to have a metric like that. Now, the trick with that is that metric is also, it's based on another statistical model that also extrapolates some people. So there is this desire to have the flywheel effect, but there is also a big danger of introducing huge bias. So I guess the answer to your question, we tried, but we're not using that. And I'm not really sure what would be like the best benefit of automating everything out there. Like, we need to be clear where the automation and inference is applicable, and where it's looks like great technical problem but not a business one. Does that make sense?
So I think it's enough. Thank you so much, Arsen.
Yeah.